In this last video of the last section in chapter 4, 4.6, we will cover Euclid's concept of area and volume. Really, we'll be talking just about area, so the area of geometric figures in the plane. And this has to do with the subject of fractal geometry, and we will cover geometric series in this video. This is something you usually cover, I believe, in Calculus 1, but if you haven't had Calculus 1, that's no problem. In this video, I'll tell you everything about the geometric series that you need to know. Okay, well, first let's define it. A geometric series is a series summing the terms of an infinite geometric sequence in which the ratio of consecutive terms is constant. So you're adding up an infinite number of numbers, but there is a constant ratio from one term to the next. So here, a very simple example. Here is an infinite sum, and this is, right here, a geometric series. Series just means you're adding up the numbers. So we have 1 plus 1/2 plus 1/4 plus 1/8 plus, and it goes on forever, ... So you know the next term would be, let's see, what would it be? 1/2, 1/4, 1/8, 1 over 16, 1 over 32, 1 over 64, and so on. Notice that the numbers are getting smaller and smaller and smaller. All right, well, another way of writing that is just like this. This makes it obvious that it's a geometric series. What's 1/2 to the 0 power? That's 1. What's 1/2 to the 1 power? That's a half. 1/2 squared? 1/4. 1/2 to the 3rd? That's an 1/8. The next term would be 1/2 to the 4th plus 1/2 to the 5th, and so on. So this is clearly a geometric series. And to use summation notation, nice shorthand, here's how we would write it. The sum, as k goes from 0 to infinity, of 1/2 to the k. So k starts at 0. That gives us the 1/2 to the 0 right there. Then k becomes a 1. That's plus 1/2 to the 1, plus 1/2 squared, plus 1/2 to the 3rd, and so on. So this is a geometric series with the first term being what? The first term is 1. And what is the common ratio r? The common ratio, in other words, let me randomly pick this one. What did I multiply the previous term by, this one, to get this term? Well, clearly, since we're just increasing the exponent, we're multiplying it by 1/2 in this case. So every term in this series can be determined by its previous term. Just multiply it by 1/2. Okay, the next geometric series is 3 plus 3/5 plus 3 over 25 plus 3 over 125 plus 3 over 525 plus ... and that pattern continues. Well, let's see. How could I write that to make it obvious that it's a geometric series? It is a geometric series. So let's see. Let me pick this term, 3 over 25. What did I multiply the previous term, 3/5, by to get this number? Well, you can see the numerator is staying the same, only the denominator is changing. So 3/5 times 1/5 gives me 3 over 25. Then 3 over 25 times 1/5 gives me 3 over 125. And then again, times 1/5 would give me 3 over 525. And then the next one would be 3 over whatever 525 times 5 is. So let's write it like we did up here. Notice now that 3 could be written like 3 times 1/5 to the 0. And then 3/5 could be written as 3 times 1/5 to the 1. And 3 over 25 can be written like 3 times 1/5 squared, and so on. So we have here 3 times 1/5 to the 0 plus 3 times 1/5 to the 1. That gets these first two terms. Plus 3 times 1/5 squared plus 3 times 1/5 to the third, and so on. I'm just going to go ahead and put plus dot, dot, dot. And we could write that using summation notation as k goes from 0 to infinity. All right, it's going to be 3 times 1/5 to the k power. So that's our second example of a geometric series. And what is the first term of that geometric series? It's a 3. And the common ratio, what number do I multiply the previous term by to get the term I was pointing at here? 1/5. So there we have two examples of geometric series. Well, we're going to be interested in finding out what the infinite sum is equal to. Again, you've probably done that in calculus, but if not, we will figure out how to sum up an infinite series. Now, before we do an infinite series, we're going to sum a finite series, a finite number of terms that we call a partial sum. So how do you find the partial sum, we could call it S, of the first n terms of a geometric series? Well, n could be the first 5, it could be 5, it could be 10, it could be 100 or 1,000,000. So this, we don't need to worry about this right now. If r were equal to 1, it would be a very boring geometric series. So you don't need to worry about that right now. All right, suppose we want to do this. S is equal to that sum. So a is just, notice, a constant term, similar to like 3 in this example up here. 3 showed up in every term. And then we have then we have r. This would be ar to the 0. This would be ar to the 1. Ar squared all the way up to ar to the n minus 1. So we have n terms because the first term starts with a times r to the 0, then r to the 1 all the way up to n minus 1. So if we're going from 0 to n minus 1, that's n terms exactly. Well, let's come up with a formula for this sum. Okay, suppose if that's the sum, then what would happen if I multiplied r by the entire sum? I'd get rs, and then on the right side, I need to multiply everything by r. So notice I'm not going to write them. I'm going to write the first term, r would be ar. I'm going to write that here, right underneath ar. So a times r is ar. Ar to the 1 gives me ar squared plus, let's see, then I would have ar to the n minus 1 plus ar to the n. So we have n terms here and we have n terms here as well. But notice that all the middle terms line up nicely here. They're exactly equal to each other. All right. So we have S and then we have R times S. Now let's do S minus RS. Okay, so if you wanted to do a subtraction problem, it would look like this, minus sign right here. So notice A to AR minus AR is 0. That's 0. That's, all of those are 0. So we're left with A there, because it's A minus 0. And then up here, we're going to get minus AR to the n. So, because we're subtracting, it's this minus this, this minus this, this minus this, all the way to 0, effectively, minus AR to the n. Okay, now we have this equation right here we're going to work with. Well, let me just observe. Well, I guess I'll do it in this next line here. What is S minus RS equal to? Well, I could factor an S out of that, right? That would become S times 1 minus R. Correct? Now, if you do the distributive property here, you get S minus RS, which is exactly that. Well, we're just going to divide both sides by this 1 minus R to get S by itself. So that would mean it gives me S by itself when I divide by 1 minus R. And then over here, I get A times 1. Let's see. Yeah, I guess I'm factoring A out of this. This would be A times 1 minus R to the n. So these equations are equivalent to each other. Dividing both sides by 1 minus R, I'll get A times 1 minus R to the n all over 1 minus R. This, is the formula. Forget this line here. That is the formula for summing up a partial sum in a geometric series. Very important formula. You'll need this. Okay, so the geometric formula, this is geometric series partial sum formula. Notice this is just capital S right here, is equal to A times 1 minus R to the n over 1 minus R. I'll circle this whole thing. I'll put a box around it. All right, almost done. Couple more special cases. The next ones, in this sum, suppose that n approaches infinity. Okay, so pretend like this really is an infinite sum. It goes on plus ... forever. Well, in that case, if the absolute value of R, that's our ratio, if it's less than 1, and what that means is R is in between -1 and +1, then what would happen to this final term right here? This one right here. Well, it doesn't matter what A is. If R is a fraction between 0 and 1, positive or negative, if you raise it up to the 10th, to the 20th, to 100, to 1,000, to 1,000,000, it starts approaching 0. So it kind of disappears. We see that the term R to the n. Yeah, let's point right here. Let's look at the right-hand side of this equation. R to the n, when R is a fraction between -1 and 1, and it's being raised to the n as n goes to infinity, that goes to 0. So in parentheses here, we'd have something that looks like 1 minus 0. So what would this fraction here become if that term went away and the parentheses just became a 1? We would get A over 1 minus R. This is the formula for summing up an infinite geometric series. Just remember, it only works when R is between 1 and -1. So it's a fraction. Could be positive or negative. That's a beautiful formula. And suppose that this first term is a 1. Let's go to the bottom, the last thing here. In this special case where the first term is 1, what would we have? Well, in that case, there wouldn't be an A, because A is just a 1. We'd have S is equal to 1 plus R, the common ratio, plus R squared, plus R to the third, plus R to the fourth, ... forever. And it would be exactly this. A would just be a 1. just the special case when the first term in the series is 1. And you can see that this sum right here could be written up above. If I factored an a out of it, it would be a times 1 plus r squared plus r to the third plus dot, dot, dot in parentheses. So this part in parentheses is what we have here. 1 over 1 minus r. And then we have times a, which is where that a comes from. So make sure you memorize how to sum up an infinite geometric series. And you remember, it'll always be the case that r is between -1 and 1. If it's not, let's say that r is bigger than 1, then most likely we're going to have a sum that just blows up to infinity, or maybe negative infinity.